All Happy Inventor videos are for educational purposes only. This episode, we are going to focus on step 1 of the invention process, which is to brainstorm ideas for creating inventions. Now, you might think that creating ideas is kind of a creative process, but really it's more of a search for problems and things that you're interested in. And so I believe this step can be taught, and that's what we're going to try and do today. Now, once you have your idea for your invention, going from the idea to the invention, that is a creative process, and we'll be teaching that in another episode. So let's get started and create some great ideas, because without great ideas, we can't create great inventions. As we research space stations, we want to pay close attention to things that users would need, or devices on those space stations that would make them more user-friendly and safer. I should point out that the area of interest you use to create your inventions can be anything. It could be automotive related, it could be aviation, toys, energy. It really doesn't matter what area you happen to be interested in. Every area has products that need to be invented. First, I will research the history of space stations to see what has already been done. And to do that, I might go to Wikipedia or the Patent Office website to look at what has been done and things that are presently being done. Second, I will also collect documents pertaining to the physics and technology of space stations, and I will collect them so that I can understand what is actually needed in a space station to keep people alive and happy. Third, I will analyze this information and see if there's things that need to be improved, or things that astronauts have complained about. Or there might be new items that people have not thought of, but you think of that would be really nice to have on a space station. We will look at all these steps, and the analyzing part a lot of times I do as I'm collecting the information. So as I'm doing this process, just kind of watch how I prepare and find information and then analyze what I'm going to do with that information. And you can do the same process with whatever area that you're researching to create an invention in, whether it's a new phone holder or a new garden hose. It doesn't matter. You use pretty much the same process that you're going to see here. There are two basic methods I use for coming up with new ideas for inventions. First, I consider what's going on around me at work and at home, and notice if there's any devices that are just irritating me, or not working properly, or just don't work as well as I wish they would. All of these are key areas where you might be able to invent something, or find an idea that could be turned into an invention. The second method I use is I do research in areas that I'm interested in, and I just simply look at what's being invented in that area, and what the technology holds. And as I research that information, I find little inventions that I could use to improve the situation in that particular field. And you can too. For this episode, I am going to actually be focusing on this second method of using an area that I'm interested in, which happens to be space stations. And I'm going to research that area looking for inventions, or rather ideas for inventions, and see what I can find. Now, space stations are not a big commodity, and may not be the greatest way to make money at the moment. However, SpaceX is producing a starship that possibly could reduce the cost of getting into space by 500 times. Now, this is a significant reduction in the cost of getting into space. And if they're able to do that, space stations might be a realistic commodity. So we don't know, but because I'm interested in space stations, that's what I'm going to study now. So let's go take a look at some of the research and the other things that are out there and see what we might come up with for ideas for space stations. So let's take a look at some of the critical systems in a space station. And hopefully as we do this and look at this information, we will come up with ideas on inventions that we can implement. Now first on the list is life support, which is obviously a critical system. You need to have oxygen being generated. You have to have CO2 being removed from the atmosphere inside the space station. You also need to remove humidity and dust from the air, because these can cause problems for not only the astronauts but for systems and electrical systems on board the space station. Now, the problem with this life support section is that it has been developed for many, many years, possibly 100 years, first in submarines and now in spacecraft. And the ISS has been operating continuously for 20 years with their life support system providing the needs for the astronauts there continuously for those 20 plus years. So can we actually develop something better than what NASA has come up with and the contractors that have produced these different systems and optimize them over the last 100 years? Probably not. So this is one of the areas that I'm going to kind of skip. I do not want to invent in the life support system unless something comes up, but probably not something I want to do just because of the difficulty, and the technology is so advanced that it would be very difficult to find new and improved versions of what's already there. Not to say there isn't, and there probably is, but for my work that I want to do right now, I'm just going to pass on it. So let's go on to the next step, or the next item on the list, and that is the living quarters and the accommodations for the astronauts and possibly tourists on board the space station. Now, you're going to have, toilets and kitchen appliances and things like that, and if you don't have gravity, this is going to be more complicated than if you do have artificial gravity. If you have artificial gravity, you might be able to use some appliances that already exist. And NASA has developed a number of appliances and systems for zero gravity. And so again, this area is fairly well developed, and possibly you can think of some areas or items that might be very useful in space that hasn't been thought of yet. And I'm sure there's hundreds and hundreds of them. But again, I'm going to skip this area because it's not something I have any idea for after going through a lot of the literature out there. I simply don't see any inventions that come to mind, and so I'm going to skip this one also. The next systems are emergency systems, and these are critical for any space station. And what do you do if something goes wrong? What do you do if the hull is punctured? What do you do if there's a fire? So you have to have fire suppression systems, and you have to have pressurized safe rooms so that you can go into very quickly and protect yourself from accidental pressure loss inside the space station. Besides that, you might design some quick sealing hulls. I don't think NASA does this yet, but maybe they do, so that if there's a puncture from, say, a meteorite or some space junk that punctures the hull can self-seal so that you don't lose much atmosphere, or it significantly slows down the loss of air inside the space station, giving you time to fix the problem. The space station, or the International Space Station, has had this problem from time to time, having a puncture that they have to locate in which compartment that it's actually in and see if they can fix it. If it takes too long to fix it, they just seal off that compartment until they can get around to sealing it back up. Thus, safety systems are a key component of any space station design. And every space station design will have its own unique problems and issues that I'll have to deal with. And space station shielding for radiation and for debris impacts, both will have to be considered from the onset to protect the inhabitants and provide them safe and secure living quarters. Thus, I may decide to invent a few things in the emergency system category. Now let's consider the radiation shielding. Radiation shielding is incredibly important because radiation is damaging to the human body. And in low Earth orbit, radiation is not that high, and very little shielding can protect the astronauts. However, as you go up into the Van Allen radiation belt, which is between about 1,000 kilometers and about 30,000 kilometers, you have much greater radiation dangers. In fact, the radiation is extremely high, and you really don't want to spend more than a few hours in that radiation belt. Now, as you move out past that radiation belt, you get into basically interstellar space, where you are dealing with the radiation coming from our sun and cosmic radiation coming from our galaxy. Now, this radiation is much higher than what is in very low Earth orbit, but still not crazy amounts. However, galactic cosmic radiation is very hard to stop. It's very high energy. It can pass through many feet of material, and so it's harder to protect from. And in fact, most spacecraft do not try and protect from this, because adding, say, a half a foot of steel to protect you from the radiation actually increases the radiation hazard, because the cosmic radiation hits the steel and then spews out neutrons all over the place. And so you have to have enough radiation shielding, which is usually over half a meter of steel or the equivalent, to start reducing the radiation that you're actually experiencing. So in general, from material to material, the radiation blocking effect is more or less the same. There are some materials that are better than others, but as a general rule, we'll want about 10 tons of material per square meter on the exterior of our space station to block the majority of the radiation. And this 10 tons is a good rule to go by. For example, above us in the atmosphere, we have approximately 10 tons of air protecting us, and it blocks most of the radiation. If we have 10 tons of steel between us and the outside per square meter, we also have very good protection. However, we may want a little bit of neutron absorbing material on the inside of that still to reduce the number of neutrons reaching the interior. So for the stations that I'm designing, I'm looking at a fairly thick portion of the outer hull being steel to block most of the cosmic radiation, and then having maybe soil and water on the inside to absorb neutrons and also reduce the amount of radiation coming in. Doing that, we can get quite a bit of radiation protection, almost the same as here on Earth. Now, do you want 10 tons of material per square meter? Well, if you only have 6 astronauts, that's going to be a lot of material. But as you scale up and get to larger and larger space stations, this amount of material really becomes necessary for the strength of the hull, and per person it's not that much weight. And so you have the advantage of scale going on here. And as we work through the numbers, we'll see that we can actually have very good shielding, very good strength for our space stations, and very low cost per person for living within that space station. So let's go on to the next topic, which is shielding against impacts from outside. Basically space junk and asteroids and small particles that are just in space but very spread out. We have to protect our craft from that. And one way to do that is to provide a sacrificial shell around your space station that may only be a millimeter thick, but particles and space junk up to about a centimeter in size, when they impact that at very high velocities, which generally in space are going to be above 17,000 miles an hour, you're going to have an impact that's not anything like a bullet. But space junk that's moving at 17,000 miles an hour or more or less, it explodes on impact with anything. It has so much kinetic energy that just the impact with a millimeter of steel or aluminum cause it to completely vaporize. Thus, if you have a sacrificial layer of metal that's a foot or two away from the main hull of the spacecraft, as that space junk hits that surface, it vaporizes itself and the sacrificial metal layer. And that vapor is moving at high speed towards the hull still, but it's expanding in both radial size and time that is going to be hitting the hull, and spreads out the energy impact over both time and space, so that the actual energy per square centimeter is actually fairly low. And so you don't damage the inner hull. So this is what NASA does also with their spacecraft. They have a sacrificial outer layer that small asteroids and particles and space junk can impact against and basically vaporize before they get to the inner hull. And we will probably be doing the same thing with even large space stations. But for large space stations, we may not even be worrying about the smaller stuff. And, well, we may still have a 1 millimeter thick outer layer that protects the outer hull, but then we might have a 10 centimeter layer to protect us from the large stuff. And using the same principle, an asteroid hitting at 20,000 miles an hour, when it hits that 10 centimeter thick piece of steel, it's going to vaporize and turn into vapor. And then you might have a spacing of 10 meters or more for that explosion that happens to basically expand and reduce the impact energy at the hull. Now, you should realize that these impacts are almost like TNT going off when they do the impact, and it's actually a directed explosion, because as the impact happens, the explosion is going to go out and fan out towards the space station still. But because you have that spacing, that explosion does not do much damage to the spacecraft. So that's kind of things we're going to think about, and I've already thought about some of them and how we can prevent damage from impacts from items that are just floating around in space at very high velocities. Now let's take a look at the next item on our list, pressure containment. This is something that all space stations need to excel at, because if you lose structural integrity of your spacecraft or space station, you're in trouble. And so this category, we are concerned with the space station actually staying together and holding not only the gas pressure within it, but also the pressures and forces caused by the rotation of the space station and its mass. And surprisingly, the air pressure is a significant portion of that stress on the outer hull of the space station, and is often more than the stresses caused by the rotation of the mass of the space station. So we'll be looking at that and airlocks, and do we put windows on the outside, and what causes problems with the strength and integrity of a rotating space station. And we're going to break this up into basically two different categories. We're going to have an axial rotating space stations, and then we're also going to have transverse rotating space stations. For example, if you have an axial space station that's a cylindrical shape, and its outer rim is rotating at a speed to give it 1 g of acceleration at that outer rim, then 75% of that space station will be in a gravitational field between 1/2 g and 1 g. In other words, the outer half of that space station is going to be greater than 1/2 g acceleration. And this is good if you have a lot of people that you want to keep healthy and keep them in a strong gravitational or acceleration field to keep their bones strong, their organs strong, and such and such. A cylindrical space station like this also has 25% of its volume at 1/2 g or less. And so this is good if you want to have low G water parks, or perhaps manufacturing where you want to be able to move heavy items around easier, because with a lower acceleration field, things are lighter. You can move them easier. Or if you're actually manufacturing in 0 G, you would need to be right in the center of the space station. So axial space stations have the advantage of providing more volume with a higher gravitational field, or simulated gravitational field. Transverse axis space stations provide a more even distribution. If at the outer edge of the transverse space station is 1 g, if you move halfway up that pipe or cylinder, you're down to 1/2 g, and when you get to the center, you're at 0 g. So half the volume of a transverse space station, providing its cross-section is constant, will have 1/2 g or greater acceleration. And the other half, the inner half of that space station, will have 1/2 g or less. Now this would be useful if you want to have more volume of your space station with low gravitational acceleration, such as, say, NASA wants to train their astronauts how to work on the moon without having to go all the way to the moon. And you could have several floors in this space station that simulate the gravitational acceleration of the moon. And so on and so on. The transverse space station also appears to be easier to make in smaller volumes, because you can essentially make the space station in a long tube, and you can get out to a longer distance that is rotating more slowly and still getting 1 g of acceleration. Where if you're this wide with a cylindrical space station, you're talking about a huge space station already. But if you just have a small cylinder that's rotating like this, then you can have a much smaller volume, a much smaller mass for the space station, and thus much lower cost and a lower number of people that actually have to live in that space station to make it economical. So there's many things to be considered, and as I've probably said before, I'm going to be working out spreadsheets to calculate these numbers so that we can adjust numbers here and there and test different things to see what works and what does not work. Our next requirement for a space station is artificial gravity. Now, you wouldn't know this from NASA that artificial gravity is absolutely necessary for living in space, but for any long-term society or any kind of exploration around the solar system, you're going to have artificial gravity, because there are just too many medical problems associated with zero or near zero gravitational fields. And thus, we're going to have artificial gravity. And the only way we know how to produce it in any efficient way is to rotate a space station to basically generate centripetal forces and accelerations that our body will perceive as gravity, and will keep our cells and our bones and our eyes and every other portion of our body healthy. So one thing we're going to do is definitely rotate our space station. And as we do that, we've already talked about rotating it axially and rotating it transversely. And we'll be looking at both of those in the next episode to see which one is better or worse. And I'm going to be putting together spreadsheets that are going to calculate all the forces on these space stations and allow us to adjust the numbers and test different things to see what works and what doesn't work, and also find out what amount of mass per person is actually going to be needed to create a working and livable space station. Creating electrical power is also an issue on a space station, because in general most of the space station is probably going to be powered by electricity. And because of that, we have to generate the electricity somewhere. Now, most space stations to date use solar panel, and these systems generally have very long lifetimes, which is nice, and they're fairly compact. Of course, the solar panels are not compact after they're extended, but they're compact for actually transit into space. Now, the other option is to actually have a nuclear reactor, which would require radiators to provide the cooling for the reactor. And to date, no one has really done that, but it is an option. And later in the future, we will be able to probably have fusion reactors, which become critical if we're going to try and travel to other stars, because as we get out into the outer reaches of our solar system, solar energy becomes weaker and weaker and actually does not become an option for powering systems on a space station. So at that point, nuclear fission and nuclear fusion will be probably things that we'll be looking at. But for our studies right now, I'm not going to even get into that. I'm going to try and power my systems or stations with solar power, because that's a very common method, and maybe having nuclear thermal-ionic systems for backup. So that's kind of what we're going to look at for space stations, and we'll be considering some of those designs also. The final area we're going to look at is thermal management. And this can be a problem for space stations, because on the sunward side of a space station, temperatures can easily reach 200 degrees Celsius, while on the wayward side facing open space, temperatures can reach minus 200 degrees Celsius. This is a problematic temperature range for a spacecraft to undergo. Now, most space stations up until this point have been fairly static in space and may be rotating once every 90 minutes as they go around the Earth. And going into the shade, coming back into the sun, they have to deal with extreme temperatures on their surfaces. Now for rotating space stations that are producing artificial gravity, this is not quite as much of a problem because most space stations are going to rotate at least every 2 minutes and probably a lot faster. For practical ones in the next several decades, you're looking at rotation rates of 1 minute or less. And so you don't have a lot of time for your space station to heat up on one side and cool down on the other. And so the amount of insulation needed can be much smaller than, say, for the International Space Station, which may have one surface facing the sun for 45 minutes or more, and giving it plenty of time to heat up and cause problems. Now, for cooling and keeping the interior at the recommended 70 to 75 degrees, we will probably have to have some heat pump controls going on. But in principle, for a very large space station, you can actually control the reflectivity and the emissivity of the surface on the outside so that you collect the right amount of heat to maintain a particular temperature on the inside. Now, emissivity, that's a fancy word for radiating heat out of a surface. And reflectivity, of course, is like a mirror. You're reflecting solar radiation away. So those two things can be separately tuned for the same surface, so that instead of having 200 degrees and minus 200 degrees, as the heat sinks in and averages out, you can pick the temperature that you actually want it to be at on the inner surface. Now, a space station that's very large needs very little heating. Skyscrapers are this way. A large skyscraper generally, even in the wintertime, does not require any heating because the heat from computers and lighting and all the accessories that are inside the building provide sufficient heat to keep the building warm even in extreme cold weather. So large space stations are going to be the same way. They're not going to need heating. They're going to need cooling. And luckily, deep space is at a temperature about 2.6 Kelvin. And so if you put radiators out, they can radiate heat away very effectively, though you will need a large surface area if you have a large heat load that you have to dissipate. And so the large space stations that I'm going to be looking at here shortly in the next episode are going to require some significant cooling to keep the interior at a reasonable temperature for the inhabitants. Now, if we add farms to our space station, this gets extremely difficult because farming and growing plants and things like that take an immense amount of energy, possibly as much as 50 times more than just humans living and working in their office are going to use. In fact, the amount of food for one person requires almost a consistent and constant 40 kilowatts of power, which is way above what would be used on the space station. As we don't need transportation anymore, just elevators are going to work. So a person on a space station may have an average usage of 500 to 1,000 watts of power, much lower than here on Earth where we need heating and cooling, while on a space station we will just be pumping chilled fluid around the space station to cool it. Thus, it's very likely that we will put farming in separate space stations just because of the immense amount of energy that has to be generated to produce the light for them to grow, and also for the cooling that has to be done so that the space station doesn't suddenly heat up to several hundred degrees and cook all the plants. So these factors that we've went through is what we're going to be looking at as we're designing these large space stations. And I'm going to start with the large space stations first because they're more fun and I'm more interested in doing those. And so in the next episode, we're going to be looking at specific space station designs and trying to build them large and just see what happens when we build these space stations large and how much structure do we actually need, how much strength do we actually need, how much shielding do we actually need. And so stick with us for the next episode and keep inventing.